So, welcome to the Martin Audio webinar training. I'm Ben Tucker, Product Support Engineer here at Martin Audio. Today, we're going to look at Display 2.3 for Scalable Resolution. This is for O-Line and Wavefront Precision products. Today is going to be an overview of Display 2.3 with specific reference to the Wavefront Precision systems and O-Line. Much of what you'll learn today is also applicable to using display for MLA, but with the main difference being Wavefront Precision utilizes external icon amplifiers with the option of scalable resolution, whereas MLA systems are self-powered full resolution solutions. More on this later in the training. So Display 2.3 is free to download by the Martin Audio website upon registration. It's our proprietary software for Martin Audio, Wavefront Precision systems, and MLA, and O-Line. It's a revolutionary and patented approach using an extremely accurate computer model of the array to analyze the system performance in a drawing of the venue to calculate precisely the parameters for the system in order to get exactly the coverage that has been specified. Numerical optimization to define cabinet angles and DSP coefficients, and a straightforward workflow from venue design to optimization output. DSP coefficients for the optimized array can be loaded into icon amplifiers, and in the case of MLA, directly to the arrays themselves. So the user interface, there are two UI modes, Basic and Expert. The default UI for new users is Basic, and today's training showcases this default UI. Basic will cover the vast majority of system optimizations that you will ever encounter. The Expert mode opens up additional parameters for the advanced user to adjust. A user can change the UI mode via Help, Preference Edit, UI mode, and then selecting the appropriate level. So the workflow is very simple. What we input into Display 2.3, venue data, sound design objectives, array details. This is in the form of the array type and size. We draw a venue slice, define the audience criteria, mechanically optimize the array, mechanical data information, optimize the array numerically, and export array preset. And the output we get from the software is an optimized array preset, which we load into the amplifiers, mechanical data, ease data, and 3D wireframe drawings. So the workflow. When we first open up the display, we get this dashboard. So along the top, we add arrays, we have basic filing parameters, we can export, and we have a help window. Next to that, we have 6 tabs, the first being a slice where we create the venue geometry, audience area, and the predefined array. Next, we define the audience coverage, non-audience areas, SPL, reference point, and dB relative to the reference point. We then optimize the array mechanically. We then check the mechanical data of the array. We optimize the array numerically, and then we check the results. And then we can export to ViewNet, which is our proprietary control software for our systems, or we can export modeling data. So in order to do this, what we first do is we click on the Add button. And we can choose here from 6 different types of products. Today we're going to look at WPM, and we're going to look at flying it. So for this tutorial, we're going to look at flying 10 cabinets. WPM and WPC we can fly up to 16. I just want to say a quick note. Sorry about the email notifications that may pop up during this. We're quite busy in the office today. So anyway, back to where we were. We're going to look at flying 10 cabinets. We'll just give it an array name WPM, and then we click the Add button. Then we can move on to our slice. What we get from our slice is we draw a rough shell geometry, fine-tune the geometry to precise venue measurements, modify or add points if required, add a predefined array to the simulation, in this case it's 10 WPM flown, and define the audience area. So when we first click on the new slice, we can define the maximum workspace for the project, or we can input an existing venue geometry if it's been created previously. What we want to do at this stage is make sure the slice is large enough to fit the venue geometry, but we can change that later. So here we can see we've changed it from the default of 14 by 40 to 12 by 30, and then we hit OK. Here we can see this is the first window we get upon slice, and we have a points list down the left-hand side there. and these can be edited once the shell has been drawn. We have the array position, so this is the height and the relative horizontal position from the rear wall here. Then we have a survey mode. Survey mode can be used to enter coordinates using angle and distance from a single point of origin within the venue. Vertical offset allows for measurements taken off the ground with a laser fitted to a tripod, for example. And then we have the shell. So starting from the left of the workspace, the bottom corner, this is used to roughly define the venue slice. Then we can snap the view in both in the horizontal, vertical, and both at the same time to an appropriate size of the shell we've created. Then we can add an array. So in order to do this, you just click the array button and then place it within the slice diagram. And to add a vertex, what we can do is just click on the little plus symbol there and drop it in anywhere along the shell and it will pop it in. Equally, what we can do here is remove one by clicking on the red button and hitting one of the numbered tabs in the drawing and it will take it out. So the points. We have an approximate vertex points to define when drawing the venue slice. Figures will be different to the ones displayed below. And we can adjust the X and Y coordinates to the exact values measured or from the drawing section. We can adjusted vertex points we can see below. So on the left here we can see this is roughly drawn. Then we've edited them so they are in following with the drawing or true measurements of the venue. We do this just by clicking on the first one and we can tab along nice and easily. And then we can add an array to our slice. So all we do is hit the array button and drop it in and fine tune the positions there. And then we click the add audience button and this will be placed on the ground plane to define the start of the audience area. And we follow it right up until the rearmost audience point, which is 27 meters or 0.8. And you click done. And then we move on to the coverage tab. We define the audience and non-audience areas and the SPL target in coverage. So the audience offset, display needs to know where the audience ear height is. Standing uses an average of 1.6 meters and seated 1.2 meters. If there is a mixture of listening heights, floor standing, balcony seating, then unchecking the uniform offset and applying the changes will allow you to do this. When the slice was drawn, an audience area was specified. This can now be adjusted by clicking on the type and adjusting the regions where applicable. In addition to the audience, non-audience option, there is a parameter called hard avoid. Apply this area to where you need to significantly reduce the SPL. Hard avoid works best if the regions are small and close to each other. Display will automatically choose no audience areas for the regions not specified in the audience and select hard avoid on the stage area behind the area. However, as mentioned above, these can be adjusted. We have the audience offset here. Now we will adjust the regions to represent a typical audience scenario. The highlighted area shows that the balcony front, floor level, ceiling, and back wall are currently audience areas. These need to be changed to reflect the actual conditions. So what we do here is we click seating to change the uniform offset for a seated audience. And then we uncheck uniform offset. This allows us to adjust regions individually. Click on the non-audience and then click under the balcony ceiling. Make sure that you click the dashed profile between points, not the colored dots. Here they're changing from green to red. And then we move on to the display tab. Display allows us to adjust the array position, change the box quantity, and then it optimizes the array mechanically. So in display, down the left-hand side here, we can see the inter-element cabinet angles, which will update after the array has been optimized. These can be manually changed after the optimization if necessary. And next, alongside that, we have the array diagram. This shows the footprint of the array and will update in real time when mechanically optimized. Then we have the coverage window. This window shows the array position and the vertical coverage limits of the array. And down the right-hand side, we have the calculation. First of all, we have aim. aim is the angle of the array determined by the optimization. This can be overwritten as well if necessary. And the height of the array, this allows you to change the height of the array if necessary. And then the X position, this allows you to change the position of the array reference from the left side of the venue. So we can see here on the left hand side, we click the optimize button and then we get the result on the right diagram. The cabinet angles have changed, as has the design aim of the array, and it now covers the audience area very nicely. And to move on, we just click done and we click on the rigging tab. So with the rigging tab, we can check mechanical data, weight and safety of both WP and O-line. We choose between 1 or 2 rigging points for WP, or choose between wall mount or flown for O-line. And we can adjust the flybar mountings of the front and back of WP, or choose whether we want to ground stack or fly it. So the full diagram, this is a scale representation of the array showing the shape, the top and bottom of the array inclination relative to the surface below. Then we have the cabinet angles in the middle there. Then we have the aiming. This displays the calculated array angle plus the angle of the bottom cabinet, which may be easier to measure if the flying grid is not fitted with an inclinometer. If a single point pickup is used, it will show which hole of the frame to use and the array angle. Please note that the array angle may not be the same as the 2-point pickup. I'll show you this in a bit more detail later. And then we have loading down the bottom. This displays the rigging information, including the total weight and loads on the front and rear points when 2 points are selected. If any of the points say fail, then the array is very unsafe to rig. And the mounting options in the middle there. So we can mechanically change the array here, whether we want to ground stack or fly it, whether we have a touring or install frame, or whether we're using a 1-point lift or a 2-point lift. 2 points obviously gives us unlimited adjustment, as long as the load on the motors is calculated to be safe. And back on the array diagram here, we can see that the link grid between the first WPM is where display determines the height of the array, and it shows us the center of gravity in the form of that yellow dot there. With O-line, we can see, again, it's a scale representation of the array showing the shape, the top and bottom of the array, and the inclination. The cabinet angles again in the middle there. The aim is exactly the same as previously. And the loading, again, is exactly the same as the WP. If it says fail, then please do not rig the array. And the mounting options, we can change whether we want to fly or wall mount it, the height of the array, and the X position. Again, we have the height of the flybar and the top of the array, and the tieback position for the O-line. And the rig, so we can choose from the drop-down menu whether we want to fly or mount. So we're going to choose keep it as flown today. And then we're going to select an install bar. The graphic will change to show the flying frame change. Select a 1-point pickup. And you can see on the diagram on the right-hand side here that it's now changed from 3.5 degrees. The nearest aim is 3.9. This is due to the position on the one hole position on the frame. So all we do is we click nearest and it will jump to that. And then we move on to the EQ. So the EQ, we can set importance criteria for audience, non-audience, and hard avoid areas. Environmental conditions, we can set box resolution, numerically optimize the array. We have air absorption compensation here. For non-optimized O-line, we have getting starting point EQ settings. So scalable resolution. Resolution is decided by the number of boxes, 2 amp channels. So WPM, we can choose between a 4-box resolution. So this is 4 boxes per 1 amplifier channel, 3-box resolution, 2-box resolution, or a 1-box resolution. So here we can show how well the resolution works. This is a standard array preset, and the red diagram shows the audience front. We have the mixed position in yellow, the back row of the audience in green, and rejection behind the speaker in blue. This is representative of the hard avoid. So you can see it's a fairly uneven frequency response, and there's minimum rejection behind the speaker. As we start to move to optimization, we can see that the frequency response starts to get a bit more linear. There's more consistency in the SPL, and there's slight improvement in the rear rejection. As we move to 2 box, we can see again it's increasing consistency in SPL and in frequency response, and yet further improvement in rejection behind the speaker. And then 1 box, we can see it's very, very consistent in both SPL and frequency response across the audience areas. And the rejection behind the speaker is very, very good indeed. This part in display, the main difference between MLA and Wavefront Precision takes place. The MLA systems are full resolution all of the time, whereas Wavefront Precision systems offer scalable resolution and optimization. So here we can see that we have environmental coefficients that we can change here, and we have the resolution. So for WP systems, you can choose how many cabinets are driven from a single circuit. This allows you to choose the resolution of the optimization. So the default for WPM is 2 boxes per circuit. If we want less than that, we can change to 3 box and then 4 box. If the resolution isn't divisible by the number of boxes in the array, then the extra boxes will have their own circuit. Then we can click more if we want to change it to a 1 box resolution, which is the max resolution for WPM. For this exercise today, we're going to choose 1 box. If we're using O-Line products without scalable resolution, we have a passive EQ button. This will give us a little window which will give us a starting point, EQ points that we can enter in, which compensate for the array shape, but obviously do not allow for any room correction. Consider these as the voicing EQ for the array. And for scalable resolution products, we just click Optimize. And during the optimization process, the software displays a non-optimized index plot and frequency response. And once finished, we can see that the frequency response is tightened up quite considerably. And we can see we have an accurate index plot there of the optimization. And then we click Done and move on. So to evaluate the results, we click on the SPL tab. And we can see immediately that the frequency response and SPL targets are very, very consistent through the venue. And here we have a diagram of our venue slice. And this little star here represents a virtual microphone that we can move to any of these points around the room and see how the array is behaving. So we have the 3 types of regions also displayed here. We have audience, non-audience, and hard avoid. And this is a standard frequency response graph from 50 Hz to 16 kHz along the x-axis and SPL along the y-axis. The average response is shown in white, the response at the reference point in yellow, the response at the cursor position in the index is displayed with its colors determined by the region it is over, audience in green, non-audience in red, and hard avoid in blue. The index plot displays the SPL at all positions in the value as color, yellow being the loudest running through the color spectrum to blue at its quietest. The horizontal axis is frequency and the vertical axis is the position around the venue shell. The white dashed line is the audience start position, and the solid white line is the audience finish. The black dashed line is the reference position. By moving the cursor up and down the plot, the position is indicated on the venue diagram and the frequency plot at that point is displayed on the frequency response graph. So let's do an optimization using display 2.3. Does anyone have any questions at this point about the display? If you just pop them either in the questions tab or the chat tab. So I'll quickly just load up our display graph here. We can see here is the display tab that I've opened up earlier, and we'll start building a display file. So first of all, what we do is we click Add. And then we choose our array. So today we're doing WPM flown 10 boxes at WPM 10. And then we click Add. Then we can move on to our slice. Oh, at the minute we're displaying this in feet. It's because I'm currently working on a project in America, and they are still using imperial measurements. I'll just quickly change that. I'll show you how to do that. If we click on Help, click on the preference edit and check the metric box. And when we click back on the slice, it's changed to meters. So what I'm going to do, I've already created the shell, so I'm going to load that in. So to do that, we click load, open up a file, and we see here we have an array, and then we import. So this shell is the base of the venue we're just working from. And we can see that we have from points 1 to 11 working in an anti-clockwise fashion all the way around, and they are displayed here. We can edit these just by clicking and changing measures and just tabbing through if we want to. We can add a point just by dropping it in, and we can remove a point just by hitting the red button and taking it back out. Let's add an array to this and let's put it at 5 meters, and then we can add an audience area. So let's pop that in all the way up there like that, and then we click done. We move on to our coverage tab. So like I said previously, we can see that from the audience start to the audience finish is all considered an audience area. So we want to change the back wall to non-audience. So to do that, we click on non-audience, and any area we don't want, we just click on the dashed line. And we now have a non-audience area. And then we want to change the top layer to seating. So we uncheck uniform offset, click the seating tab, and drop in on the dashed line, and we can see that dropping down now. And once we've achieved that, we just hit done and move on to our display tab. So here all we want to do is just hit optimize and watch the array mechanically optimize. You'll see there it does a little dance whilst it works out the optimum angles. And we can see that it's covered the venue pretty well within its parameters. So all we do now is we click done and move on to the rigging page. So here we can see the full diagram of the array with the array height, the bottom of the array, center of gravity here, and its X position along the bottom. We have the array angles in the center here and the detailed diagram of the venue. So what we want to do now is we want to change the frame type to an install bar, and we'll see the graphic change. We'll change it to a 1-point hang, and you can immediately see that the design aim is incorrect, and we want to change it to 6.7 degree, which is nearest hole would be 1, and all is green, so we can continue. So we move on to EQ now. So we can see an unoptimized index plot, and we can change environmental conditions here and the resolution here. Today we're going to work in a 1-box resolution. So what we do is we hit more to get to 1 box, or we can go all the way down to 4, 3. As I've said, the default is 2, and we go to 1, and then hit optimize. Now the array will numerically optimize in terms of getting its frequency response and coverage consistent as possible all the way through the audience areas, whilst maintaining good reduction levels and non-audience and hard avoid areas. So this can take a bit of time depending on the array type and the resolution. So a large hang of WPC, for example, which is a biamp box in 1-box resolution, is going to take a lot longer to optimize than an array of 10 boxes of WPM in 2 or 3-box resolution, or even 4. So we just let this happen, and we can see it working its way through the frequency spectrum there. At this point, if any of you guys have any questions, I'll be happy to answer them. There will be a handout of this PowerPoint presentation available for you guys afterwards, which will be emailed to you. And you can also get a copy of this webinar if you would like it. As I said, this can take a little bit of time to optimize because there's a lot of DSP processing going on here. If you have large arrays that you're wanting to optimize, you can always hit the optimize button once your parameters are in, go make yourself a cup of tea or a coffee, come back, and it should be done. And this optimization will give us a set of EQ filters which will be considered the optimized EQ curves, and they will be loaded into our icon amplifiers, which will determine how the array behaves within the parameters that we've told it to. So we can see straight away that the optimization is tightening up the SPL throughout the venue, and it's keeping it very consistent across the frequency range. So as I previously said as well, WPM has a resolution of 1 to 4 box. WPC, we can do 1 box resolution, 2 box resolution, or 3 box resolution. And O-Line products, we can do anywhere from 1 box to 8 box resolution. The great thing about scalable resolution is if you want to buy one, or if you have one of our Wavefront Precision systems and you don't have enough amplifier channels to work at the higher resolution, you can always work with a lower resolution and then purchase amplifiers later, and it's all one nice package. Okay, now the hue optimization is done, we can see the index plot has changed as previously mentioned, with the yellow down to the blue with the highest to the lowest SPL, and we've got a nice consistent frequency response through the slice. We just click done now and we can review that in more detail in the SPL tab. So what we can see immediately in the top right is the consistency of the SPL and the frequency response through the slice, with our audience average response shown in white, the reference response in yellow, and as I've previously mentioned, when we cursor through the index plot, we can see this blue line will change from blue to red to green depending on which surface we are looking at. So let's do that. So we see that we start at the back of the venue going up the rear wall, and we can see there's a very heavy drop off in frequency response and SPL on the non-audience areas, and start to come into play as we hit that audience area there. It's very consistent already in SPL and frequency response, even with a long throw. And then as soon as we hit the balcony drop, we can see the HF dropping off there and it getting quieter until we come back into our audience zone. And as we come down the venue, we will see it getting louder, but the frequency response will stay very, very consistent. And there we are now hitting our reference point and getting a bit louder as we get to the front. It's very consistent all the way through with minor variations in frequency response. And then we hit the front under the array, it'll drop off considerably and into the hard avoid area. So that is what we expect the array to behave like in this space. And what we can do is export the optimization EQ and the files and load them into our icon amplifiers. We can also add comments here to the display file. If we want to model different arrays within this, we specific little comments saying audience start, we're focusing more on the hard avoid or non-audience or anything like that, which will just remind us. And we just click done and we can save that now. We'll save that into my display 2.3 folder as WPM 10. And we can save. And then to export that, all we do is click on the export tab here and we can get a printable mechanical report, a drawing, a wireframe drawing of the array, export to ViewNet, which is the one we want to look at, or we can export 3D data for ease. So what we do to export to ViewNet, we click on the export tab, pick our export route. So I'll drop that in my display 2.3 folder. We'll give it a file name. So that's WPM10 settings is absolutely fine. We can save that. We can click the array here. If we have multiple arrays within this file, we'll see them all along here. We can check and uncheck which arrays we want to export. And then we just hit export and we'll watch it. It'll export the different DSP channels out and it's done. And now if we go into this folder, we can see a DTP file, which is the export to be loaded into ViewNet.